they're saying that A plus B, you can commute it. Now, all properties, when you're dealing with matrices, all the properties that you deal with when you're dealing with real numbers, they don't all apply for matrices. But in addition and subtraction and associative properties, those all work, because you can do those things. And then you have a zero when you add. So this is the additive identity element, and that's the matrix that has all zeros. And then you can multiply a scalar times A plus B. Now, you can do a scalar times A plus B, but you cannot do a matrices times A. You have to be really careful when you're doing multiplication, because sometimes it won't work. So it's not a general. So you have two scalars and you have a matrix. I guess they've used A, but it'd be the same difference. And then you can, when you have this, you can associate that. You can do the scalars first and then multiply it times your matrix. So those properties, they're just real, we're comfortable with those because that's what we're used to in the real numbers. And then they're going to go through some proofs. But now when you get to matrix multiplication, they're going to, this is where you have to be careful, because it isn't going to be intuitive like, when we do multiplication in real numbers. And the definition there on 97 says, a matrix that has m by n, m rows, n columns, and if B has n times P matrix, then the columns of B1, B2, so on. Now, notice you can do, I just want to back up, you can do that multiplication. You can do the multiplication this way. When this is an m by n, and this is an n by p. And you can do the multiplication as long as these two are the same. But you see, if you put it the other way around, only in special cases, if you did B times A, then you'd have an n by p and an m by n, and you see these two don't necessarily have to be the same. They would have to be identical to do the multiplication. Because when you do this multiplication right here, and you do this multiplication here, and you have m by n, n by p, the result is an m by p matrix. But you see, this can only be done, this one, when n p equals m. If p does not equal m, you cannot do that multiplication. So commutative property multiplication isn't always possible. And it's probably not going to give you the same result even if it's possible. So, does that make sense? So the intuitiveness of how you go from real numbers, commutative property, and associative properties of multiplication is not going to apply. And that definition is just saying that if you do a matrix multiplication A times B, it's the same as if you take the columns. If you break that B down into B1, B2. I don't even want to put commas in that. B1, B2, and whatever it is. When you do this A times B, it's the same as doing A, B1, A, B2, A, B3, and so on. So you can do this one. At the bottom of the page, it's telling you in that paragraph right above example 4, just what I've tried to tell you right here. It says the number of columns in A must match the number of rows in B in order for linear combination such as A, B1, or for either one of these two things that I've shown you to be defined. Okay. So on the next page on 98, it says row column rule for computing AB. If the product AB is defined, now notice it's saying if it's defined, then the entry in row I and column J of AB is the sum of the products of the corresponding entries in the ith row of A and the column J of B. So they're just saying that if you have A and B and you want to get this position right here, then what you have to do is you have to have this one here times that first one, right? And that will give you, if there's 1, 2, 3 rows and there's 1, 2 columns, then if this is the second row, first column, then you have to have multiplied this row times first column to get it. That's all they're telling you there. And then on 99, the theorem 2. Now notice they're telling you that you can do association that's going to be associative law multiplication is okay, and you can do a distributive law. Ace. And then you can also do this where you go B plus C A. But you cannot, these two are going to be different. You cannot say that A times B plus C is equal to B plus C times A. That won't work. Because when you do this, those are not necessarily the same, and they might not even be doable because your columns and rows might not match up, or rows and columns. So that's what I'm saying, is that the whole thing when you're dealing with real numbers in matrices, it doesn't transfer over. So you want to be real careful about doing that. And then you can do scalars. You can do that. R times AB. And you can multiply R times A and then do your B. Or you can do A and do your R times B. That'll work. But notice that it's R is a scalar. It's just a number out in front of the matrix where you're multiplying every one of the items in that matrix times that R. And that's different than multiplying a matrix times a matrix. So does that makes sense? Okay. Now, they're saying I sub m A equals A equals A I sub n. Now notice that these are not the same. Because when you do it the right, your multiplication is the row of I with the column of A. When you're doing it on the left, it's the row of A times the column of I. So you're not, these things have to match up. But the identity element is always that element that has the ones down and it has zeros. That's always the identity element. It has a diagonal of ones, and the diagonal runs that way. It does not run this way. It runs this way for the identity. Okay. They're giving you a warning once again on 100 that you be very careful that the commutative law of multiplication, A, B, when it's matrix, it's a real special case when this is true. So in general, that is not going to be true. Only in special cases is that true. And then it says the calculation laws do not hold for matrix multiplication. That is, if you got A times C is equal to A times B, then you can't do this. And therefore get C equals B. That's not true. You can't do that. C and B can be different matrices, which is it's not intuitive. But you have to be aware that that's the way it is. And then this other one, there's another thing that doesn't follow intuition. If you got A, B matrix multiplication that equals 0, and then you got A, C multiplication that equals the 0 matrix, then you would generally say, well, B has to equal C has to equal 0. That's what you generally conclude, and that's not true. You can get a B matrix when multiplied by an A gives you 0, or a C matrix that gives you 0, and those two don't have to be equal to each other. I mean, it's just counterintuitive. So just be careful when that's what makes linear algebra and matrices really confusing. At least to me, it's just counterintuitive of what you do with rules and when you're dealing with real numbers. Now there's going to be transposes that you do, and transposing something, if you notice just that this is what a transpose is. They're saying that if A equals A, B, C, D, if you do transpose, then it's A, C, B, D. And notice what they're doing is the column becomes the row. The column becomes the row. So this is first column, second column, then it becomes first row, second row. That's a transpose. And then the rules apply. If you got A transpose, and then if you transpose that, you get A, right? So if you go from here to there, and then you go back up here, you're just right back to where you started from. And then A plus B transpose is A transpose B transpose. Now those two are fairly intuitive, right? I mean that's what you would think. And the next one is what you would think would work. If you go RA transpose, when you have this thing, then you could factor out your scalar and do A transpose. And those are going to be equal. Because it doesn't make any difference whether you multiply the scalar times the matrix and then transpose the rows and columns, or if you transpose the rows and columns and then multiply by the scalar. It's fairly intuitive. What's not intuitive here is this next one. A, B transpose equals B transpose A transpose. You know, we would like to do what? We would like to say this is A transpose B transpose. It's not the case. So that's counterintuitive. So you cut it. You have to watch the theorems, watch the problems, and kind of remember that certain things work the way you intuitively like to have them, certain things don't. And you know, I'm not teaching this class and trying to teach you how to prove. I'm not, you know, maybe that would be another teacher that would say you got to prove things, and that's probably really at the graduate level that you do that. And that's what, if you ever think about going on to graduate school in anything, then you start taking all these theorems and you start proving. And that's what that's all about. I always thought when you went to higher math that you just kind of kept developing upon what you've learned in the past. Higher math is you prove that 2 plus 3 equals 5. You prove it based upon assumptions and hypotheses and theorems and things like that. Then you prove that that's true. That's when I got out of theoretical mathematics and went into applied mathematics. That's confusing. It's more confusing than matrix algebra is to me. So, All right, any questions on that? So we have to be careful. In addition, it's going to be fairly intuitive most of the time. But in multiplication, you have to be careful about things that run counterintuitive. So I'm going to look at page 102, and number 2. Okay, it says they're giving you these matrices, A, B, C, D, E, and then they want you to calculate A plus 2B. Now the first thing you want to do is, in order for the matrices to be added, their rows, columns have got to be equal. In other words, M has got to, this should be something else. M's got to equal A, and N has got to equal P. You have to have the same number of rows and columns in both matrices. So if you notice, A is a what? 2 row, 3 column. B is 2 row, 3 column. Can be done. Notice, could you add A and C? No. So now you could multiply A and C, but you couldn't, because C would have to be three rows. You could multiply CA, couldn't you? Because you would have 2 columns in C and 2 rows in A, and that'd be doable. So what we'll do is we'll do A is 2, 0, minus 1, 4, minus 5, and 2. And then it's plus, and it's a scalar 2 times the B, 7, minus 5, 1, minus 4, and minus 3. Now we want to do that scalar times that second one. So it's 2, 0, minus 1, 4, minus 5, 2. And then that scalar times it means we multiply every term. 14 minus 10, 2. I hope that's a 1. 2 minus 8 minus 6. Now we add them together. So we'll go 2 plus 14, then 0 minus 10, minus 1 plus 2, 4 plus 2, minus 5, minus 8, and a 2 minus 6. So you're just adding the column and row, so that the result is going to be 16 minus, is that 10, and then a minus, no, plus 2. And then it's 6 minus, what's that? Yeah, thanks. It's a plus 1. Then it's 6 minus 13, right? And then minus 4. Now number 2, the second one, they're saying do 3C minus E. And first you want to look at C and E. Is that even possible? You see, a C is what? The rows and columns, it has 2 rows, 2 columns. Then E had better have what? 2 rows, 2 columns. And E has 2 rows, 1 column. That's not possible. Does that make sense? Okay. Now they got C, B. Now, what you want to do is you want to make sure that your columns in C match your what? Rows in B. Because, see, this, if this is N, M times N, then this has got to be N times P. These have got to be the same. So the columns in C must match the rows in B. Do they? They do, right? So you can do that multiplication. So C is a 1, 2, minus 2, 1, and B is a 7, 1, minus 5, minus 4, and a 1. A 1 minus 3. So this is a 2 by 2, and this is a 2 by 3. By 3. So I better come up with what? A 2 by 3, shouldn't I? Better come up with this as a result. So for this first one right up here in the top, I multiply the row times the column. So it's 7 plus 2, right? And I'm going to go across. And the next one, it's a minus 5 minus 8. I'm taking this row and then the columns. So then it's the next one over is 1 minus 6. And then I'll take this row times each one of these columns. So then it's minus 14 plus 1, and it's plus 10 minus 4, and then it's minus 2 minus 3. So if I've done all my stuff right, it's 9 minus 13 minus 5 minus 13. What was that number? 10 minus 4 is 6, and minus 5. So that if I've done all my multiplication right, that's what it should be. Okay, the next one they're asking to do is EB. So the E is what? It's a 2 row by 1 column, and B is a 2 row by 3 column. So what do you think? It's not possible, right? You see, this one and this one are not the same. Not possible. Number 4 is saying do A minus 5I 3. Now, I3 is 1, 0, 0, 0, 1, 0, 0, 1. That's the identity I3. So if we do A, this is going to be 9 minus 1, 3 minus 8, 7 minus 6, minus 4, 1, 8, minus, now what I'm going to do is I'm going to run that 5 through this identity matrix here and put it here. So makes this thing 5, 0, 0, 0, 5, 0, and 0, 0, 5. Now I could have put a plus and made that a minus. I could have done this way. And maybe that's easier to see. So what I'm doing is the result of that operation is I'm going to add 5 to them, I'm going to add these two, right? This is how it's going to alter this. Okay, so I'm just going to write the result down here. The first row, first column is going to be 4, and then it's going to be minus 1, 3. Then it's going to be a minus 8, and I'm taking a minus 5. 7 minus 5 is 2, and then it's a minus 6. And then it's a minus 4, 1, and 3. And that's, now then let's do, it's saying do 5 I3 I'll put the brackets. 5 I3 A. So that scalar 5I3 is actually going to be 5, 0, 0, 0, 5, 0, and 0, 0, 5, right? And then the A is going to be 9 minus 1, 3, minus 8, 7 minus 6. Okay. So we'll do this times this, put it in this position right up here. So 5 times 9 is 45, right? Minus 0. It's 0 times a minus 8 is 0. 0 times a minus 4 is 0. So the next one, when I do, to get this position, I'm multiplying this one times this one, right? And so it's a minus 5. And then likewise, this is 15. And then the next one, I'm multiplying the second. So it's going to be this one times this, and so on across. So the 9 don't go, but it's 5 times a minus 8. And it's 5 times 7. And then 5 times minus 6. And now the last one I'm just going to multiply it. I think that was 4, isn't it? That was, this is a minus 4, so it's 5 times a minus 4 is a minus 20, 5, and 40. Now notice that this is the same thing as if I did I 4 times 5 times A, right? It's just multiplying every one of those terms. I does not, when you multiply by I and it has ones, it will not change the matrix. So that's, okay, 5 and 6. It says compute the product AB in 2 ways. By the definition, when AB1 and AB2 are computed separately, and then by the non-column rule by computing AB. So 6. Four minus 2 minus 3, 0, and 3, 5. B is 1, 2, and 3 minus 1. Now understand that this says B1 is 1, 2, and B2 is 3 minus 1. Okay. And then what they want us to do is AB. They want us to do A, B1, and then AB2. I'll do this. 4 minus 2 is 3, 0, 5, 1, 2. Now notice it's possible because the number of columns in A is the same as the number of rows in that B, in that vector. So it's going to be a 3 by 1 result. So this is going to be 4 minus 4. And then the next one is minus 3 and 0. And then the next is 6, oh, how about 3? 3 plus 10. So it's 0 minus 3, 13. If I did my multiplication right. And then my A and this vector is the B one, so it's 3 minus 1. So then it's 12 plus 2. And then it's minus 9 plus 1 plus 0. And then 9 minus 5. So this is 14 and minus 9 and 4. So the result, when you put B1, B2, it's 0 minus 3, 13. Now, it better come out this way when I do it AB, right? Which problem am I on? 6. So I got 4 is 2 is 3, 0. And B 1, 3, 2 minus 1. I forgot enough room. So notice this is a 3 by 2, and this is a 2 by 2, and the 2's match. We're good. We're going to have a 3 row, 2 column. So right up on the top left hand corner, it's going to be 4 minus 4. And the next one over is going to be 12 plus 2. And in the middle it's going to be minus 3 plus 0. And then it's going to be minus 9 plus 0. And it's going to be 3 plus 10. And then it's going to be 9 minus 5. So what I have, 4 minus 4 is 0. 12 plus 2 is 14. Minus 3 and 0 is a minus 3. Minus 9 and 0 is a minus 9. 3, 10 is 13. And this is 4. Now it should be the same, right? It's this one right here. And this one right here. So just showing us that it don't make any difference whether you multiply the vectors or multiply it out matrices. You're going to get the same thing. All right, 10. So we go to a quarter to 11, right? says let A equal that matrices, B equal that one, and C equal that one. Verify that A times B equals A times C, yet B is not equal to C. So these are just helping us understand that those theorems are true. So if we do A, B, two minus 3, 4, 6. B is 8, 4, 5, 5. So up here it's 16 minus 15. And then it's, hope that's a 4. 8 minus 15. Then that's a minus 32 plus 30. And a minus 16 plus 30. So this is 1 minus 7 minus 2 and a plus 14. And then AC. So this is 2 minus 3. 6. So this is 10 minus 9, and then minus 4 minus 3, minus 20 plus 18, and plus 8 plus 6. So it's 1 minus 7 minus 2 and 14. And they just, these two are the same, but these two are not equal. So it's just showing you the counterintuitiveness of this multiplication. And if you did real numbers and you did that, you would be able to show that B equals C. Well, in matrixing multiplication, it's not so. They're just giving you an example. These two are not equal, but these two are. And these two are equal. Those two aren't. It just goes against your intuition, right? Says let A equal 3, that matrix. Construct a 2 by 2 matrix B such that AB is the zero matrix. Use 2 different non-zero columns for B. All right. This there can be a lot of these matrices. What they want to show is that A times B is a zero matrix. So I want to make sure I do this thing right. Okay, what we're going to do is we're going to have E is going to equal so that B1 equals 0, 0. And B2 is 0, 0. So if we say A, B equals the zero matrix, then A, B has to equal 0. In other words, this thing minus 6 minus 1 and 2 I did this wrong. I was going to do it wrong. X1, X2, and X3, X4. And that has to equal 0, 0. Okay. So what this is saying is that 3x1 minus 6x2 has to equal 0, and a minus x1 plus 2x2 has to equal 0. And so what we can see from this is that if we do, this is kind of like inspection, that x1, x2 a 2, 1 would be possible if we multiplied 2 times 3 and got 6, and 1 times a minus 6 right here, substitute in, and then that's going to be true. And then what you can do is you can use any multiple of this. you could have x1, x2, as long as they were in the ratio of 2 to 1. See if you went 6 times, put 6 in here. 3 times 6 is 18. 6 times 3 is 18 equals 0. And then if you put 6 in here and 2 times 3. So you could do anything as long as the ratio was like that. And so what the conclusion is that if you take this matrix 3 minus 6 and minus 1, 2, you multiply it by a matrix 2, 1, and 6, 3, that's one possibility that'll get you a 0, 0, 0, 0. But as long as you do, if you do any of those columns with a ratio of 2 to 1, it'll come out right. I mean, you could have a 2, 1, 8, 4, or you could have a 6, 3, 8, 4. As long as it was in that combination, that would get you the 0 matrix. And there's just not a let's say it's kind of an inspection problem. It's not a problem where you solve it. You just kind of got to look at it, see it, and then kind of intuitively say, okay, this is what has to happen. It says if A and B are 3 by 3s, and if B is B1, B2, B3, then A times B equals 3. So A, B, 3 by 3s. Now, just the first thing is just by observation. What is that matrix? The A is a 3 by 3. This is a 3. If this one right here is a 3 by, well, A is 3 by 3. B1 is actually a what? 3 by 1. So that AB is a 3 by 1, right? You could do the same thing here. This is a 3 by 1, and this is a 3 by 1. But now, what are you doing? You're adding 3 by 1s, and the result is going to be a what? 3 by 1. That's written incorrectly. See, this should be written this way. A, B1, A, B2, A, B3. Then you got a 3 by 1, a 3 by 1, and a 3 by 1 put side by side, right? Understand? They've just written it. When they write it plus in there, they're making a 3 by 1 matrix. But if you put a 3 by 1 here, then you're putting 3 elements like that. And then if you put a 3 by 1 here, you're putting 3 elements. And if you put a 3 by 1 here, and then the result is a 3 by 3, right? But when you do a 3 by 1, you got 3 elements here. And then you add one's like this. And then you add over here. What you do is the result is a matrix here that if this is A and this is B and this is C, is A plus B plus C, right? It's the way they wrote it that makes it incorrect. You're not going to get the result that you expect. Now it says the second row of AB is the second row of A multiplied on the right by B. So that true or false? They're saying this. So A is second. This is B. See, it's the column of A. The resulting matrix is that thing, right? Multiplied on the right by, right? So, but it's saying the second row of A is the second row of A multiplied by, on the right by B. Well, that's got to be false, right? It's okay, then C says AB times C is AC times B. What's wrong with that? AC. See, in order to go from here to here, what you got to do is you got to go A, C, B, right? And that's not possible because it's not. You cannot commute these two in multiplication. So that's false. And then that D part, where it says A, B transpose equals A transpose B transpose. Well, look at that theorem. And what does that theorem say? It says A, B transpose is equal to B transpose A transpose. So this is not true. So this is false. Okay. Number 20, I'm about out of time. Number 20, suppose the second column B is all zeros, what can you say about the second column of AB? It's also all zeros. So that's